sorry, so I'll make another one. The logarithm is the inverse to the corresponding exponential. So what does that mean? That means if you see an equation in exponential form, you can rewrite that equation in log form by just remembering that logs undo exponentials. But if you can go one way, of course, you can go the other way. Both of those mean the same thing. And we have some like algebra laws for exponentials. Presumably those correspond to some algebra laws for logs. And let's try to talk about why we should even want such things. So let's remember one thing that we got out of logarithms. If I asked you to solve 5 to the x is equal to 7, you can just solve that, right? What's the solution to that equation? Let's see. Is that an equation that's in exponential form? So that means you can translate from exponential form to log form. So on this side, you see a base of 5. So you can translate that to log form to see that the log, base 5 of the thing on the other side, 7, is equal to x. Oh, hey, neat. That just solves the equation, doesn't it? Right. I mean, maybe it seems artificial. Really what I've done is I've just given the solution to that equation a name. I've called it the log base 5 of 7. But now you can have a computer compute. And some of the things the computer needs to compute that are some rules that govern what logs do. But maybe we'll motivate this rule instead by thinking about solving a more complicated equation. So there I see the equation log base 2 of x squared plus 1 minus the log base 2 of x plus 1 is equal to 2. Is that equation of the form log of something is equal to something? Oh, maybe I should ask this question too. I handed out notes before everyone was here. Does anyone not have a copy of the notes? Cool. There's a stash. Anyone else? Okay, we're good. Presumably there's also some other stashes of notes in the back. I'll grab them after. Oh, no, they're at the front. Thank you.
Oh, there's probably other places too.
Yeah, because that's not very many. I think I overprinted by a lot. So let's talk about how to solve an equation like this. So do I see, is this an equation that's already in log form? Is it just log of a single thing is equal to something else? Well, it's not, right? It's log of something minus log of something is equal to something else. I can't just rewrite this in exponential form. It's not in log form. So I need some like algebraic rules that tell me how I can put this side in log form so that I can rewrite it in exponential form, and hopefully that'll help me solve this equation. And what are those rules going to be? Well, here, there. These are the things that I will call logarithm laws. The first one you already know. For any base b, the log base b of 1 is equal to zero. And there's a good reason for that. Right? Logs undo exponentials. So let's think about the corresponding law for exponentials. For any base b, b raised to the power 0 is 1. So if b to the 0 is 1, that means the log of 1 must be 0. So the remaining rules that we'll try to get are the following. What is the log base b of x times y? What's the log of a product? What's the log of x divided by y? And what is the log of x raised to the y? We'll try to figure out each of those. And each of them will be motivated by a corresponding rule for exponents. So here's a rule for exponents. What's b to the x times b to the y? B to the x plus y, because what is that? It's b written down x times in a row, then you write b down y times in a row, so that's b x times x plus y times. Similarly, what's b to the x divided by b to the y? What about b to the x raised to the y? And right now, let's kind of focus on the first one. So, right, log is supposed to be like the opposite of an exponent. And so what this rule says is that if you take a product of exponentials, Gesundheit, what do? You wind up just adding the numbers and the exponents. Sorry, b to the x is an exponential. The thing in the exponent is the x. So the log should do something opposite. So instead, if you multiply two things inside of a log, maybe what you'll wind up doing is adding the logs. That seems reasonable anyway, and we will totally justify it in just a second. So, maybe that didn't seem intuitive to you, but let's justify that rule by computing the log base b of x. And I don't know, here's the way that maybe we'll think about it. Even if you don't believe that formula up top is true, I should be able to say what the log base b of x times y is if I know what the log of x is and the log of y is. That seems reasonable, right? So let's take the log of x and the log of y. Let's give them names so that I can know a thought of them. What would you like to call the log of x? Give me a variable name. How about star? If you don't want to call it star, don't call it star. You guys just didn't tell me anything, so I just picked something. So maybe you would rather call it a letter, like C. What would you like to call the log base b of y? Smiley face will take me too long to, well, circle is a bad choice because that's like 0. Yeah, so maybe I am stuck with smiley face now. All right, tell a variable what you want to tell a variable. Oh, wait, cool. Is this an equation that's in log form now? So I can rewrite that in exponential form. I can rewrite that as x is equal to b to the power of star. Similarly, if log base b of y is smiley face, then what is y equal to? B to the power smiley face. I'll put an upper caret just to make sure I remember that that's in the exponent. Right, same way as you would type into a computer. B plus smiley face. Well, wait, now I know what x is and I know what y is, so can I just write down what x times y is? Yeah, right, I'm going to use bigger symbols now because I've used poor choice of variable names that I can't draw small. B to the star times b to the smiley face. Oh, wait, but what's b to the star times b to the smiley face? Oh, well, wait. Now check this out. Now I'm just going to summarize this step. So that means that x times y is b to the star plus smiley face. Is that an equation in exponential form? Yeah, I see a thing is equal to a base raised to a power. So that must mean that the log base b of what I see on the left-hand side is equal to star plus smiley face. Now, on the one hand, that should make you happy. I wanted to know what the log base b of x times y is. There's what the log base b of x times y is. But the answer involves star and smiley face, which were artificial variables that we made up midway through our analysis. What is star equal to? Star is equal to? Good. And what is smiley face equal to? That's the log base b of y, isn't it? Oh, cool. So the log base b of x times y is the log base b of x plus the log base b of y. And there's even a proof. That is what it has to be equal to. How do people feel? People feel okay about that? Nice. So now that we have this formula from a little bit of mathematical abstraction, let's use the formula. So maybe I should tell you what I want the takeaway for today to be. The first main takeaway is what are these three formulas. There's the first point of today. The second point of today is how do you use the formula. So let's use the formula that we just gained to achieve some things. Let's compute the log base 3 of 2 plus the log base 3 of 1.5. So, on the one hand, well, what is the log base 3 of 2? Is that a number that you can just know? No, that's 2 to the 3. Right, so the log base 3 of 2, so that's like, what power do you need to raise 3 to get the result of 2? So like 3 to the 0 is 1, which is too small. So it's bigger than 0. But 3 to the 1 is 3, which is too big. So that number is somewhere between 0 and 1. And part of the point of today is I don't want to care what the decimal approximation is, but I've stalled long enough that you guys can probably tell me what the decimal approximation is. What is the log base 3 of 2? It's not 2 thirds really, but what's its decimal approximation? It's somewhere around 0.6. Right, so it's not actually equal to 2 thirds. On the other hand, what's the log base 3 of 1.5? Approximately. By using a machine. Right, so I mean, we can think about it the same way. 0 is too small and 1 is too big, so it's something between 0 and 1. Somewhere around 0.36. And I guess that was like 0.63 something? Okay. Well, then I guess this should be a 7, if I'm rounding correctly. And what do you get when you add those two things together? 1. And maybe there's some like rounding error. So maybe the answer should be 1. You guys got more digits than I did, so maybe you actually got something more believable as 1. But let's try to convince ourselves that it has to be 1. Let's think about the log law that we just got. Do I see in that quantity a sum of 2 logs with the same base? So that means I can rewrite that as a single log where I just multiply together the two things inside. So this is equal on the nose, not approximately, but equal on the nose to the log base 3 of 2 multiplied by 1.5. Oh, what's 2 times 1.5? 3. Without using a machine, you know that that's 3. And it's not approximately 3, it's equal to 3. Log base 3 of 3. Oh, but what's the log base 3 of 3? 1. So even though there's no way without using a machine to know what either of those numbers are, you can compute their sum on the nose exactly. So there's one takeaway from logarithms. You can use them to make computations. Maybe I'll stall for a second and say, well, here's another one. I think I asked this on Wednesday also, but how many people have actually seen a slider rule? Oh, none. Okay. Well, if only some people have kind of seen a slider rule, I assume that no one in this room has ever used a slider rule. So all the slider rule consists of is like 3 wooden bars. They don't have to be wood, I guess. Where the top and the bottom are fixed in place, and the bottom one you can slide across. And you slide across the bottom one in order to achieve addition. And when you start with the information on the bottom and where the middle ends up, that tells you on the top what the result of addition has to be. That's all logarithms can really do. They can only add. That's all slider rules can do. They can add. Oh, but hey, you remember how I also mentioned that like old-timey engineers would have had just books that contain logarithm tables and exponential tables? So here's what they would do. They want to multiply together 2 numbers. Well, they say, well, screw that. Multiplying is too hard. Instead, I'll use this book that I have to look up what log of b is and what log of y is. I know how to use the slide rule to add those together. Now I'll go not to a log transform book, so that'll tell me what the log of x times y needs to be. I'll go to an inverse log transform book, which you know what the inverse of log is, it's an exponential, but those are also hard to compute on your own, so they would go to a book which contains a table of exponential values. They would say, well, if I know then what log of x times y is, I'll take the inverse log transform to figure out what x times y is. So that's the way that old-timey engineers would multiply together big numbers. In fact, that is what a computer does if it wants to multiply together two really big numbers efficiently. That's right, addition is an easier algorithm than multiplication is. So if you want to have a computer add things together, teach the computer how to compute logs and exponentials, and then use this rule. But that's maybe getting a little bit divorced from the content we can actually hit. This isn't a coding class, so I can't have you like implement addition and multiplication using a computer. No, I mean that's a good thing to learn how to do. So let's instead try to do some algebra. Let's try to solve this equation. Log base 3 of x plus the log base 3 of x plus 1 is equal to 2. Let's solve that. So, first things first. Well, we can't use the trick that we would want to use. The left-hand side is not in, the left-hand side isn't just log, a single logarithm. If it were, then I could rewrite it in an exponential form and maybe my life would get easier. But can I rewrite the left-hand side so it is a single log? Do I see a sum of two logs on the left-hand side? Yeah, so I can use this rule. I can say, well, that means that the log of thing plus the log of thing is the log of thing times thing, where thing and thing are whatever it says up there. So the log base 3 of x plus the log base 3 of x plus 1, that's the same thing as the log base 3 of x multiplied by x plus 1. Now is that an equation that's in log form? Sure is. So, let's take this equation in log form and rewrite it in exponential form. So, right, there's the base of the exponent. So if I take log base 3 of thing equals thing, I should be able to write it as 3 to the power, the thing on the right-hand side of the equation. Oh, no, down here. Log base 3 of thing equals y. This should become 3 to the power of thing is equal to whatever's in the parentheses. So rewriting it in exponential form, what will I get? I'll get x times x plus 1 equals 3 to the power 2. People feel pretty good right now? Does that make sense? Well, let's simplify. What is 3 to the power 2? 9. If it were just like 0 on the left-hand side, that would make me kind of happy because I know how to solve a product equals 0. I would set each of the individual things to be 0, but it's not, so I can't. So instead, let's expand out the left-hand side and see what it is. What is x times x plus 1 when you expand it? X squared plus x. So I wind up with x squared plus x equals 9. Is that an easy equation to solve? Yeah, it's like a quadratic equation. So, I mean, I'll stall for a little bit while I rewrite it as x squared plus x minus 9 equals 0. But now, like, what tool do you have that solves any quadratic equation? You have a formula for the solutions. And at this point, you guys have even like used the formula enough that you haven't memorized it, right? I'll conclude that x is, well, I don't want to do any more thinking. I want you guys to just tell me what goes next. What is x? And I'm doing this one in like all the detail because after I get the solutions, there will be a subtlety. So I want to get those solutions first. So I guess it'll be x is equal to negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. So that's negative 1 plus or minus the square root of double negative becomes a positive, and 4 times 9 is 36. So inside that parenthesis, I see 37. And then I need to divide by 2. So I see two solutions to this equation. Well, let's just do a quick check. Let's check whether both of those are even in the domain of consideration. So let's do a quick domain check. Excuse me. Thank you. Let's check domain. So I see x inside of a log. What numbers am I allowed to put inside of a logarithm? What's the domain of log? Positive things. So since x appears inside of a logarithm, x had better be positive. X plus 1 also appears inside of a logarithm. So x plus 1 had better be positive. Fair enough. But if x is positive, is x plus 1 automatically positive? Yeah, so there's the domain in consideration. Are both of those numbers positive? Well, let's see, root 37, that's like pretty close to 6, right? So if I take 1 and subtract a number that's pretty close to 6, will I get something positive? No. And division by 2 won't help me. So only x equal to negative 1 plus root 36 all over 2 is a valid solution. So that's an important thing to check. And fundamentally, why is it that that badness could happen? Well, let's look at what's inside of this log. I see x times x plus 1. If x and x plus 1 are both negative, what can you tell me about x times x plus 1? It's positive. So you can take an invalid input and get a valid input in the next step. So you change the problem a little bit when you do this. That subtlety makes sense? So what's the takeaway? Make sure to check your solutions are actually in the domain of consideration. They might not be. So there's how you can use that first logarithm law to do some algebra. And I think I'll skip the derivation for the next. So if log of a product is the sum of the log, what do you think the log of a quotient is? Subtraction. Log of x over y is the same as the log of x minus the log of y. Log of x over y is the log of x minus the log of y. So instead of trying to explain why it's true, the explanation is the same as it is for multiplication. Let's try to use this formula to achieve some things. So let's skip the technical and abstract seeming bit, which is why is this formula true? Let's jump straight down to some computations. Let's use this to compute the log base 5 of 15 minus the log base 5 of 3. And maybe first let's just do a sanity check. Is the log base 5 of 15 a number that you can just know without using a computer? Let's see, I know that 15 is between 5 to the 1 and 5 to the 2. So log base 5 of 15 should be like 1 point something. Log base 5 of 3, I definitely can't know. But let's use this rule. Log base 5 of 15 minus the log base 5 of 3 should be the same thing as the log base 5 of 15 divided by 3. Oh, what's 15 divided by 3? 5. So this will be the log base 5 of 5. What's the log base 5 of 5? 1. Nice. So just like the rule for multiplication, you can use this rule for that subtraction goes to division to compute a difference between two logs, even though you can't know what either of those logs are equal Similarly, let's use it to at least make it a chunk of the way through solving this algebraic equation. Log base 2 of x squared plus 1 minus log base 2 of x plus 1 is equal to 3. Fair enough. Well, is that already an equation that's in logarithmic form? Not quite. All right, log form means you have something in the form log of number equals number. And I don't quite have that. I have log of number minus log of number is equal to number. Oh wait, but how can I rewrite log of number minus log of number? What's that the same as? That's a silly thing to ask. What is the log of x squared plus 1 minus the log of x plus 1?
X squared plus 1 divided by x plus 1.
It's the log of x squared plus 1 divided by x plus 1. And it does matter what the base is, even though I wasn't saying it. Oh, neat. Now do I just have log of thing is equal to number? So I can rewrite it in exponential form. And without even doing it, will rewriting this thing in exponential form make my life a little bit easier? That's good. So that means I can rewrite this as x squared plus 1 divided by x plus 1 is equal to 2 to the power 3. How many people almost rewrote that instead of 3 to the power 2? Okay. That's an easy mistake to make, even if you didn't make it in this case. It's something to keep in your mind when you're doing these computations. Make sure you keep the base as the base. But what is 2 to the power 3? 8. 3 to the 2 would be 9, but this is 2 to the 3. Cool. So 2 to the 3 is equal to 8. So I get x squared plus 1 divided by x plus 1 is equal to 8. Is that an equation that you know how to solve? Right, that's not the same as knowing the solution, but you know how to solve that equation? So I'll give you guys a choice. Do people want me to continue talking through that all the way to a solution? Okay, then I will. So let's see, if I need to solve that equation, maybe I should multiply both sides by x plus 1 to get the x plus 1 out of the denominator. So what do I wind up with? I get x squared plus 1 is equal to x plus 1 times 8. So 8x plus 8. How many people almost just wrote down 8x plus 1 on the right-hand side of that? Okay, yeah, those parentheses are important, right? Because you need to multiply the whole of the right-hand side by 8. So it's really 8 times x plus 1. The whole thing needs to be multiplied by 8. But now it's an easy equation to solve, right? That's a quadratic equation. So we can rewrite that. X squared minus 8x minus 7 equals 0. Cool. And what are the solutions to that? Well, we have the quadratic formula. So I know the solutions of that will be x equal to negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Have I successfully applied the quadratic formula? It's always hard when you actually say the names of things instead of what numbers they are. I think I wrote down the correct things, right? Okay. Yeah.
It should be negative 7.
Indeed it should. Thank you. And that's important because now this becomes plus. And on the one hand, like, there's an answer. Maybe I'll just do a little bit of simplification first. X equal to 8 plus or minus, let's see, 4 times 7 is 28. Is that 92?
Yeah.
Okay, good. And now let's just do a quick sanity check. Are both of those in the domain of consideration? So let's try to figure out what the domain of consideration should be. So I see x squared plus 1. What things am I allowed to put inside of a logarithm? Positive things. So when is x squared plus 1 positive?
Anywhere above 0.
Well, it's just positive always, right? X squared plus 1 is always positive. If you take a square and add 1 to it, you'll get a positive. So this has no issues with domain. Now how about x plus 1? When is x plus 1 positive?
Always.
Even when x is negative 10?
When it's above 0.
So I need x plus 1 to be bigger than 0. So what do you get when you solve that inequality for x? Needs to be bigger than negative 1. So these x values, they both have to be bigger than negative 1. So let's try to decide that. Are both of those x values bigger than negative 1? When I do the plus branch, 8 plus the square root of 92 over 2, is that bigger than negative 1? 8 plus a positive number, positive. What about the minus branch? What's 8 minus the square root of 92 all over 2?
Something negative.
So 8 minus root 92 all over 2 is somewhere around negative 0.7. Or maybe I rounded wrong. I just truncated it. I just stopped listening as soon as you said 7. Is that bigger than negative 1? So is it in the domain? So are both of these numbers in the domain? Yeah, there are two solutions. Both in domain. Nice. So there are two solutions to this equation. Any questions about that? Okay. So let's try to motivate this last rule before explaining why it's true. So what you see here is if you take the log of a product, like, so multiplication becomes demoted by logarithms to sums. Right? Multiplication is supposed to be like a more powerful version of addition. Log demoted it down to addition. So that means log should demote exponentiation to something that's like weaker than exponentiation. What's something weaker than exponentiation? Multiplication? That seems reasonable, right? So if log should demote x to the y down to multiplication, y times the log base b of x. And I think it's actually worth going through the argument why, and I think I'm okay enough for time to pull that off. I'll run through the exact same argument as before. So I think that the answer should have something to do with the log base b of x. So let's give log base b of x a name. What name would you like to give log base b of x? Fish. All right, well, my fish will wind up looking like an alpha anyway, so I'll probably say alpha instead. That's the good letter alpha. It might look like a fish. So if log base b of x is equal to fish, or alpha, could I rewrite that equation in exponential form now? Yeah, I'll get x is equal to b to the power fish. Well, if x is b to the power fish, then I can rewrite x to the y as b to the alpha to the y. But what's, well, fish. Okay, you said fish. What's b to the fish to the power y? B to the fish times y. Fair enough. Oh, wait, cool. So that means that x to the y, I'll treat that as a block. is equal to b raised to the fish times y, or alpha times y. Is that an equation now that's in exponential form with base b? Yeah, I mean, I guess it also looks like exponential form with base x, but I won't use that. I'll use base b. So what will I get? I'll get b, log base b of x to the y is equal to alpha times y. But what's alpha again? Or fish? What's fish? So the log base b of x to the y is log base b of x times y. Is that exactly what we said it should be? Yeah, I guess it's multiplication is done in the wrong order, but multiplication is commutative, so it doesn't matter. Cool. So let's see what the whole point of this is. We can use these rules to do some algebra. Let's solve equations. Let's try to solve this equation. 2 to the log base 5 of x plus 1 minus the log base 5 of x minus 1 is equal to 2. So first thing first, is that equation an equation that's already in log form? No. It's not. A single log is equal to another. But let's try to use these rules to rewrite it in log form. And the first one I'll look at is this. Is that a number times a logarithm? So according to the rule that we just explained, I can take a number times a log and put that number into the exponent inside of the log. So that's the same as the log base 5 of x plus 1 squared. And now the rest I'll just bring along for the ride, minus the log base 5 of x minus 1 equals 2. Is that an equation that's in log form now? No. But you know how to put that in log form. I see log minus log. What is log of a thing minus log of a thing? Log of the division of the things. So that'll give me log base 5 of x plus 1 quantity squared divided by x minus 1 equals 2. Now do I have an equation that's in log form? I do. So let's rewrite it in exponential form, and hopefully that helps. If that doesn't help, then maybe we've been barking up the wrong tree. Rewriting it in exponential form, you'll get x plus 1 quantity squared divided by x minus 1 is equal to what? 5 to the 2. And I asked you because I was really close to accidentally writing 2 to the thing, which would be 1. Oh, nice. So that means that this equation has been reduced down to x plus 1 quantity squared divided by x minus 1 equals 25. Okay, does that look like an equation that you know how to get a solution to? Yeah, you'll clear the denominator. Then you'll boil out the top, I guess. You'll get a quadratic equation. You'll use the quadratic formula. Is it automatically guaranteed that the two solutions the quadratic formula gives you will be valid solutions to the equation? No, but you can check for domain. X plus 1, that means x had better be bigger than negative 1. X minus 1, that means x had better be bigger than 1. So what's the strongest of those? X is bigger than 1? So I wrote those because I have 5 minutes. It would take me 5 minutes to do the algebra. So I'm not going to finish that computation because I want to get 2 additional formulas. And these 2 formulas are both known as the change of basis formula. They tell you how you can express any exponential in terms of your favorite exponential, and any log in terms of your favorite log. So how many people have like a preferred exponent, a preferred base for an exponent they prefer to log with? Okay. How many people have a preferred base for logarithms that they just would rather use? Because it's the one that is easiest to plug into a calculator. How many people only know how to do log base 10 in their calculator? Okay, good. I'm appealing to you guys right now. That means 10 is your favorite base for that reason. I'm going to teach you how to compute any base, and log with any base, even though you only know how to compute it with base 10. But first, I'm going to need to do that for exponents. So let's pick your favorite base, say 10. If you want b to be 10, you can imagine that b is 10. And let's try to take this equation, which we know is true, that's this rule, and rewrite it in exponential form. And let's see, is that an equation that's in log form right now? It is, right? It's log base b of a thing is equal to a thing. So that means I can rewrite it in exponential form as the thing inside the parentheses is equal to b raised to the power of the thing on this side. Oh, neat. So that's interesting. That tells you that if you want to think about a to the x, instead you can think about b to the x, except you can't just think about b to the x. You need to multiply that b by a number. A to the x is the same thing as b to the x times the log base b of a. So in terms of if you wanted to express 2 to the x in terms of 3 to the x, you would say, well, that means 2 to the x must be the same thing as 3 to the x times the log base 3 of 2. So here, what am I doing? I'm treating this number as a, and this number as b. So you can express any exponential in terms of any other exponential. You just have to be willing to multiply the thing in the exponent by a logarithm. And let's just see that that agrees with what you already know. So I'm going to just rewrite that on this side. So 2 to the x is equal to 3 to the x times the log base 3 of 2. And you'll notice here that I've told you what the log base 3 of 2 is. It's somewhere around 0.63. So 2 to the x is approximately 3 to the x times 0.63. Let's think about this in terms of graphs. So that means I can get the graph of 2 to the x if I start with the graph of 3 to the x and do what to it? What does it do to the graph when you multiply all the x's in a formula by a constant? If I know the graph of f of x, then what is the graph of f of 2 times x? You compress it by a factor of 2. All the exponents will get divided by 2. So the graph of 2 to the x is equal to the graph of 3 to the x with x values divided by 0.63. So let's see, division by 0.63 is the same thing as multiplication by a number bigger than 1. So the graph of 2 to the x is the same as the graph of 3 to the x, except it's being stretched out. That makes sense? And let's see if that even agrees. Here's the graph of 3 to the x. There's 2 to the x. Yeah, that seems to work out. The graph of 2 to the x is the graph of 3 to the x, just stretched by a little bit. And that even tells you what factor it's stretched by. So with my remaining 90 seconds, I don't have enough time to explain why the next formula is true, but I am going to use it. So here's the remaining formula. The log base a of x is the same thing as the log base b of x divided by the log base b of a. And some of you have calculators that can only walk with log base 10. Let's see what that means. That means if you want to compute, say, log base 7 of 8, well, here's something you can do. Here's the base you would like to walk with, a. Here is the number x you would like to plug in. And a base that you know how to walk with is the log base 10. So let's use b equals 10. And we'll see that this quantity is the same thing as the log base 10 of 8 divided by the log base 10 of 7. Nice. So even if your calculator only has a log base 10 button, or maybe a ln button, you can walk with any base you want by doing that. Cool. So I've gone over by a minute. I apologize for that. I haven't quite covered all the content. I apologize for that too. I'll post 2 different versions of this lecture as a video. One of them will actually cover all the content. But feel free over the weekend, think about things like the homework assigned over the course of the week. Ask me any questions. And if you want me to finish the stuff in this note packet on Monday, just make sure to ask me at the end of the day.